All right, so we're now on to Theorem 6.27, which is the Riesz-Thorin interpolation theorem. This one is long. This is the blackboard right here is just the statement of it. So we will be breaking the video up into multiple parts. This video is just the setup of the proof. So I've got the statement here, and then a couple whiteboards or chalkboards worth of set up just to start working on the problem. In the next video, we'll be actually doing the proof. It'll be broken up into possibly 2 videos there as well. But let's see if we can get through this in one shoot. So we're going to suppose that we have 2 measure spaces, x and y. Sigma algebra M and N, mu and v are the measures respectively. And then we have numbers P0, P1, Q0, Q1, and they're going to be in the closed interval from 1 to infinity. Also, for t between 0 and 1, we're going to define 2 new numbers, pt and qt, which are going to be defined by 1 over pt is equal to 1 minus t p over p naught, plus t over p1, and the same for qt, 1 minus t over q naught plus t over q1. So this is a variant on sort of the standard way that we go about shifting from one number to another. So in like algebraic topology, when we want to show that that I can map one function to, or that there's a smooth path of functions from that there's a smooth set of paths from one path to another, then path of paths, then we're going to have them do this kind of 1 minus t plus t, and then since we're starting with t at 0, we're going to start with this being valued for t equals 0 at p0, and we're going to end up when t is at 1, this is going to be 0, and we're going to be left with 1 over p1. So we're doing that kind of standard shift motion, but instead of being concerned about shifting from p1 to p, from p naught to p1, we're concerned about the reciprocal of p1 shifting to the reciprocal of p naught, and vice versa, and the same for q. So from there, we're now going to take a linear function that goes from the space of the direct sum of LP naught and LP1 to the sum of LQ naught to LQ1. So we've got a linear map. So an operator, and we're going to define these 2 numbers, m naught here and m1 here, which are going to be the bounds, right? So t of f, q naught less than or equal to a constant times f p naught, and m1 is the coefficient for our bounding for the q1 and p1. And again, for all f in LP naught and LP1 respectively. Then, lastly, we're going to assume that if q naught and q1 are equal to infinity, then we're assuming that v is semi-finite. And the reason that we're going to need that is to, during the setup to the proof, we're going to be relying on Theorem 6.14, which needs that semi-finite condition on that case for the theorem to be applicable. So those are all the assumptions. If all of that holds, then we have that QT measure of TF is going to be less than or equal to m naught negative 1 minus t m1 t of f, the piece of t norm on f for all f in LPT and for all t in 0, 1. Now, again, this is so kind of intuitively what we're seeing here is that as we shift from the p naught q naught to the p1 q1 transform using these definitions of the pt and pq, we're going to see the coefficients that we use as our that are used in the definition of the bound on the function are going to be shifting with respect to that same kind of transition where the 1 minus t and t are in the exponent. So that the operator norm is going to shift as the norms, as the coefficient, the PT and the QT shift. So that's the basic idea of the theorem. Now, we're going to start with a trivial case that is a byproduct of Theorem 6.10. So for the trivial case, we're going to assume that P naught equals P1. And we remember, as we proved a couple videos ago, that Theorem 6.10, if we have 0 is less than P, Q greater than P, R greater than Q, less than or equal to infinity, then we have that the union of the LP-LR spaces is a subset of the LQ space, and we have that the norm is bounded in this way, using this weird definition of lambda. Now, when we make P naught equal to P1, we know that Q, if P naught's equal to P1 and Q naught is equal to Q1, then the statement's obvious, right? Because it's just, because then M1 and M0 are going to be the same thing. So then their product with the exponents and t's is just going to be that M1 equals M naught equals M1. But if Q naught and Q1 are different, then one of them has to be greater. So we're going to have them be the P, then we're going to set the, one second. Then we're going to set, I wrote myself a side note on this one, just kept forgetting how to say it. Then we're going to know that QT is in between, so we're in one of these two cases. Either Q naught is less than QT is less than Q1, or Q1 is less than QT is less than Q naught. And in either one of those cases, we then have our PQR, which allows us to make the statement here. And we notice that the that what we get from this is that so then what we can get from this statement here is that lambda equals t. So we get that the norm with respect to QT is less than those two norms with the exponents, but that's exactly how we defined, if we go back to the statement of the theorem, that's exactly how we defined our M naught and our M1. So we get that that's less than, with those exponents, the product, and obviously it's less than F of P, because that was how we defined the M naught and M1 in the original statement of the theorem. So from there, what we get is that, and here we have that P is P1 or P naught. They're all the same, so it doesn't matter. So from this, we get to assume that P1 is not equal to P2, because that case is trivial from what we already proved in 6.10. So also, if we make this assumption, one of them might be infinity, but the other one can't be that. So we know that for all t not equal to 1, pt is less than infinity. Now we're going to define two sets. We're going to define sigma sub x and sigma sub y, and these are going to be the set of simple functions with support of bounded measure. So in other words, they vanish outside of some finite measure set. So the support is contained within some bounded measure set. So and we have obviously sigma x is that for x and sigma y is that for y. So we note that they are both dense in LP and and LP mu and LPV. Here, P is just any number between any positive real number. And we know that this is true because of Theorem 6.7. Theorem 6.7 tells us that these are dense within these sets. So now we want to show that for all F in sigma sub X, we want to show the result for F in this set because it's dense within the LP. So what we're going, the reason that this is that this is going to end up being useful is because of Theorem 6.14. So the statement of, can you guys see that? Let me pull this a little closer for this one, and then I'll reset it. Okay. So we have, let P and Q be conjugate exponents. Suppose that G is a measurable function on X such that the product of F and G are in L1 for all F in this sigma X set. Then we're going to define M sub Q of G, Q being, again, the conjugate exponent to P, equal to the supremum of the set of absolute values of integrals of the product of F and G, where F lives in sigma X and in the P norm is 1. So, its norm in the P norm is 1. We also assume that this MQG is finite, and the reason for that is because if it's not, then we're not going to properly be defining it. So we then assume that S sub G, which is where the values of X such that G of X is not equal to 0, is sigma finite, or we can use that mu is semi-finite. And that is the reason that we have this special case in our statement where we say if Q1 and Q0 are both infinity, then we need the norms or the measure to be semi-finite. That is why we had that statement in there originally, because we need to make sure that we're meeting this condition in that case. So if we assume all of this, then we have that G is in LQ and that the Q measure, the Q norm on G is equal to this MQG set. So taking the supremum of the integral with its product on all sigma X functions with norm 1 and P. So using that theorem, we get that TFQT, oops, gotta put this back now. Is that all within the screen? Cool. Okay. Now we have that the QT norm of TF is equal to the supremum of the absolute value of the product integrated with dV for all G in sigma Y and it in Q prime T and with G, the Q prime T norm of G equal to 1, where Q prime T is the conjugate to QT. Now note, the reason that we can apply this theorem is because we have that the operator, the image of T is a subset of Q naught Q1 by hypothesis. So we have that this here must be semi-finite. So sigma finite. Because why? Because if not, then we would have an uncountable. We wouldn't be able to cover this set with countably many finite measure sets, which would cause problems with the integral. So, and hence it wouldn't be in LQ not Q1. However, if they are equal to infinity, then it doesn't matter because we have assumed that V is semi-finite. So with both of these conditions met, we meet all of the conditions of 6.14. Because we have that it is in fact sigma finite, and we've got this set is the same as the sigma x. We just swapped the x and the g. I don't know why the book did it that way, but they set it up with here with it being here the sigma y plays the role of sigma x in the here in the statement of the 6.14. Anyway, so from this, now we take two more assumptions. So we now assume that f is not equal to 0. Obviously, the statement of the theorem is obvious. It is trivial if f is equal to 0, so we assume it's not equal to 0. Then, since we've assumed it's not equal to 0, we're now allowed to scale the FPTs to be equal to 1. So now we've got that the g inside of this definition, we have that f is F is unit in the PT norm. Okay, so that's the setup for the proof. In the next video, we're actually going to get into how to use this to prove Theorem 6.27.